Hi, everyone. Congratulations on surviving Project 2. Well, I notice, yeah. If you can handle this, then you can probably handle anything Berkeley could possibly throw at you. So feel good about yourselves. And I noticed that the class is substantially thinned out. So for those of you who are still in the labs and watching this after the fact on the video cast, my apologies. But hopefully it will be a character-building experience. I'm going to continue talking about graphs today. So I talked about depth-first search last class, and we're going to continue with breadth-first search now. So again, the idea of breadth-first search is that we want to visit every node in a graph once, but we want to control the order. And so what we're going to do here is we're going to visit some designated starting node first. You get to choose what node you start at. And then we're going to visit all the vertices that are one vertex away from the starting node, and then all the vertices that are two vertices away from the starting node, and then all the vertices that are three vertices away, and so on. And that's why it's called breadth-first search, is it sort of searches as widely as possible rather than trying to go as deeply as possible, as fast as possible, which is what depth-first search does. Now, breadth-first search is a lot like level-order tree traversal. It's not easy to write it as a recursive routine. It's much easier to write it by using a queue. So that's what we will do. We will use a queue so that vertices are visited by distance from the starting vertex. And I'm going to show you the code that does that. I was going to hand out this code, but I had a photocopier malfunction. My apologies. But this will be in the lecture notes if you don't want to try to copy it down now. The main thing I want you to do right now is just look at it. So it's called BFS for breadth-first search. And it takes one parameter, which is U, the vertex that we're going to start searching outward from. So we always start by visiting the starting vertex first, setting it to visited so we don't visit it again. So u.visited equals true. Then we're going to create a queue, and the queue initially contains only the starting vertex. After we've done that, most of the work is done by this main loop here, this while loop. And what this while loop does is over and over again, it dequeues one vertex off of the front of the queue. It finds all of the vertices that are reachable along one edge from that vertex, checks each of them to see if they've been visited or not. That's what this line does. Checks a neighbor W of V to see if W has been visited or not. And if it hasn't been visited, then we visit it. And that means doing some sort of computation on it, like maybe summing, if in our city graph, like I said, you might visit a node by summing up the total populations of all the different cities in the graph. Then we mark it as being visited so that you won't visit it again. And finally, and maybe most importantly, we add the vertex we've just visited to the end of the queue so that later on, all of the neighbors of W will get visited as well. Now, when we visit a vertex, we can do some more interesting things than just add up numbers. Here is a visit routine in the vertex class. purpose of this routine is we want to do two things. We want to actually explicitly calculate for each vertex how far is it from the starting vertex, like what is the length of the shortest path from each vertex in the graph to the vertex that we started at. And we want to actually find the shortest path, the path with the least number of edges from every node in the graph to the starting node. And so here's how we do that. The visit method takes in a vertex as a parameter in addition to the vertex that we're actually running on. So the idea is if I started at some vertex, let's call it S, and I go from there to visit a vertex U, and I go from there to visit a vertex V, every vertex has what's called a parent, which is the vertex that we visited it from. So U's parent there is S because we got to U from S. V's parent there is U because we got to V from U. And so when we call visit, we'll call it on a vertex, v.visit, and then we'll pass in its parent as a parameter. And that's what the code I showed you on the previous page does, is whenever it visits a vertex, you pass in its parent as a parameter so that you can keep track of that. And the actual code itself does two things. First of all, every vertex has a parent field. And the purpose of that parent field is just to remember how I got visited. So if I'm vertex V, then my parent field is going to point back at U. And U's parent field is going to point back at S. Like that. And what these parent pointers will do is they will give you a way to find a way back to the starting vertex from any other vertex with the shortest path possible. And we will also compute the depth of each vertex. So the starting vertex gets a depth of 0 in this parent tree. And every other vertex is assigned a depth of its parent's depth plus 1. And so that number, the depth, is going to tell you the length of the shortest path from the starting vertex to this vertex. So that's the code. Now let me animate it for you. First, let me write down the most important part of what I just said. When an edge, VW, is traversed, to visit the vertex W, the depth of W is set to be the depth of V plus 1. And V becomes the parent of W. Now, by the way, parent is not a graph term. I want you to think of this as there being actually two separate data structures here. There's the original graph, and there's a new tree that I'm building that tells you what the shortest path is from any vertex back to the starting vertex. And that tree is separate from the graph. So let's go back to our city adjacency graph that I drew last time. And I'm going to run breadth first search on this, starting from Albany. So we start by visiting Albany. And so we visit it, we set its depth equal to 0. And because it's the very first starting node, that's going to be the root of our tree, and so its parent is set to null. All right, now breadth-first search works by keeping a queue. And at the very front of this queue, I put the starting vertex right after I visit it. So right now, the only thing on the queue initially is Albany. Then I start looping, and what my loop is going to do is it's going to dequeue whatever's at the front of the queue, and that's Albany, and check all of the edges out of Albany one at a time. So the first edge we check is Kensington. From Albany to Kensington. Has Kensington been visited yet? No. So we're going to visit it. We're going to set its depth equal to 1. We're going to set its parent to Albany. And we're going to mark it as visited so we don't visit it again. And we're going to add it to the queue. And are there other edges out of Albany? Yeah, there's one going to Berkeley. So I do the same thing for Berkeley. Visit Berkeley, set its depth to 1, set its parent to Albany. Now there are no more edges out of Albany, so I'm done with Albany. I go back to my outer loop. I take whatever's off the front of the queue, out of the queue. That's Kensington. And I look at all the edges out of Kensington. Well, there's an edge from Kensington to Albany, but Albany's already been visited. There's an edge from Kensington to Berkeley. Berkeley's already been visited. There's nothing to do. So back to the outer loop, take another node off the queue. My new vertex is Berkeley, so I look at edges out of Berkeley. Well, Kensington and Albany have already been visited, but Emory has not been, so now I visit Emeryville. And I set Emeryville's depth to 2 because Berkeley is going to be its parent, and Berkeley's depth is 1. So Emeryville's parent is Berkeley. Its depth is 2, and I add it to the queue. The last edge out of Berkeley is Oakland. Oakland's not been visited yet, so I do the same thing with Oakland I did with Emeryville. And no more edges out of Berkeley, done with Berkeley. Oh yeah, and I queued Oakland, of course. So back to the outer loop. Take Emeryville out of the queue. Look at all the edges out of Emeryville. They've all been visited, so there's nothing to do for Emeryville. Do the same for Oakland. Take Oakland off the queue. Emeryville's been visited. Berkeley's been visited. Piedmont has not. So Piedmont's parent becomes Oakland, and Piedmont's depth becomes Oakland's depth plus 1. Add Piedmont to the queue. Take it off the queue. Nothing left to visit. We're done. Now, the main thing to observe here is that if you want to find the shortest route from Albany to any other city, then you start at that other city and you trace the parent pointers backwards up to the root of the tree. So if I want to find the shortest path from Piedmont to Albany, I just follow the parent pointer, follow the parent pointer, follow the parent pointer. And that's the shortest path between Albany and Piedmont, and its length is 3, which is what the depth tells me. Any questions about that? Yeah? This is not necessary, no. That's right. You can just say depth, you can just say parent. Other questions? All right. So again, the most important side effect of this algorithm is that you can find the shortest path from any vertex to the start vertex. By following the parent pointers. Why does this work? I guess I shouldn't have erased the queue. Going back to my queue. The reason it works is because we, in queue, the starting vertex first, the sole vertex with depth 0. And when we dequeue it, we enqueue all of the vertices it's connected to, and that is all of the vertices that have depth 1. Then, when we're processing the depth 1 vertices, well, any vertex that's connected to a depth 1 vertex either has to be a depth 2 vertex or it has to be already visited because it's depth 0 or 1. There's no way that you can get from a depth 1 vertex to a depth 3 vertex by a single edge, because if you could, it wouldn't be a depth 3 vertex. So, when we're processing these depth 1 vertices, that is when we add all the depth 2 vertices to the queue, and no others. When we're processing all the depth 2 vertices, that's when we add all the depth 3 vertices to the queue, and no others. And so the queue keeps the depths sequential, so I process one depth at a time. Any questions about that? All right, so breadth first search, just like depth first search, runs in big O of v plus e time if you use an adjacency list. Why? Well, I mean, if you look at the code, what does the inner loop do? It processes every edge once. Or, well, in a directed graph. In an undirected graph, it processes every edge twice. But the number of times the inner loop iterates is going to be the number of edges, or twice the number of edges. The number of times the outer loop iterates is going to be the number of vertices. And there's nothing more expensive going on than that, so that's the running time. But if you use an adjacency matrix, then in order to find all of the edges out of a vertex, you have to look at the whole row of the adjacency matrix. So that means it takes v squared time with an adjacency matrix, just like it did with depth first search, because you have to look at every entry of the adjacency matrix at least once. So where graphs get really interesting, though, and where you get really interesting graph algorithms is when you start talking about problems on weighted graphs. Now, a weighted graph is just a graph where each edge is labeled with a numerical weight. Now, those weights could express a lot of different things. They could express the distance between two nodes in a highway graph or in a street map. They could express the cost of flying from one city to another. They could express the resistance between two intersection points in an electrical network. And so graphs are used to model all kinds of things. You know, the wiring of your house, the wiring of a circuit board, the communication graph of the major airlines, anything like that. And you can assign all these different costs to them. Question? Mm-hmm. Yeah, if that's something you wanted to record. And that's probably something that, you know, the map programs that you use on the internet do record. They probably have that information. Now, the map programs on the internet probably have each edge labeled with lots of numerical weights, the expected time to traverse that road at different times of day. If they're really sophisticated, they might have that. So yeah, you could assign all kinds of things like that. So how do you represent one of these things? It's pretty easy. In adjacency matrix, instead of just using an array of Booleans, you can use an array of ints or doubles. Now, when you use an array of ints to mark weights in a graph, you still need a way of saying that the edge is not present at all. And so sometimes you might just use -1, for instance. Like if you have a graph where the edges weights represent the distances between two nodes, since two nodes are never a physical distance of -1 apart, you could just use a -1 to say there is no edge here. But there are some kinds of weights, some kinds of graphs in which negative weights are allowed, and you might not have a special value you can spare. So in that case, you might actually have two different arrays. You'd have a 2D array of Booleans that say, yes, the edge is there, no, the edge is not there, and then a second two-dimensional array of ints that say what the weight of the edge is if it is there. In an adjacency list, well, you've got these list nodes, and you can always increase the amount of information you store in a list node, so store the weight there. In addition to the reference to the destination vertex. Now, there's lots and lots of different problems you can study on weighted graphs. And if you take CS170, you'll study a bunch of them. Two of the most common problems are what are called the shortest path problem. We actually just studied a very simple version of the shortest path problem. We studied the shortest path problem when the weight of every edge is 1, and you just want to find the path with the fewest edges in it. But more generally, if these edges represent distances between faraway cities, and you're looking for the shortest route to drive from one city to another city, then you need to use weighted edges and not just assume that every pair of cities is 1 mile apart. And so that's where the shortest path problem comes in, and you will study that lots if you take CS170. What we're going to look at today is the other most famous problem called the minimum spanning tree problem. Now, in a minimum spanning tree problem, you have something like, well, let me give you an example. Suppose that each node of the graph, well, suppose you're trying to wire your house for electricity, and each node of the graph is either an outlet or there's one special node that's the source of electricity. And maybe what you'd like to do is wire them all together so that all the outlets are connected by some path to the source of electricity using the shortest length of wire possible. So you have a graph that connects these different nodes together, and the edges of the graph are labeled with the length of wire you would need to connect them together. And so our puzzle is, how do you connect all the nodes together with the shortest length of wire? question. Yeah, yeah. Well, so Lagrange multipliers, as I understand them, which isn't very well, are mostly used in numerical optimization problems. And this is more of a combinatorial optimization problem, meaning we're not looking for an optimal point in a continuous space. We're looking for an optimal choice when you have a finite set of choices. And so I think they're very different problems. So there are a bunch of algorithms for this problem. We're going to study one by a guy named Kruskal. For finding a minimum spanning tree. And, well, I guess I want to first formally define what a minimum spanning tree is. So let's suppose we have G equals VE is an undirected graph. There isn't really a version of the minimum spanning tree problem for directed graphs. It's pretty much always done on undirected graphs. So then a spanning tree of G is another graph, which I'll call T, which has the same set of vertices but a different set of edges. And normally it has V minus 1 edges of G, because that's how many edges it takes to connect V vertices together into a tree. Now, that's the usual case, but there's sort of a special case, because the graph that we started out with might not be connected. So if G is not connected, then T is not actually a tree, because it can't be. T is actually a bunch of trees. And a set of trees that are disconnected from each other is called a forest. Now, for the rest of this lecture, I'm just going to assume that G is connected and make all my arguments based on the assumption that G is connected. But take my word for it that the algorithm that I'm going to show you works just fine if G is not connected, and it gives you the minimum spanning forest. Now, if G is weighted, then we can define a minimum spanning tree. Well, a typical graph, if it has enough edges, can have a lot of different spanning trees. So we want a special one. So what's a minimum spanning tree? Well, first of all, it has to be a spanning tree. And second of all, when you add up the weight of all the edges it uses, that has to be as small as possible. In other words, there is no other spanning tree of G that has a smaller total weight. So here's Kruskal's algorithm. It computes the minimum spanning tree as follows. We start by creating a new graph. With the same vertices as G, but when we start off, there are no edges. Then we're going to make a list of all the edges in G. Now, Kruskal's algorithm is what's called a greedy algorithm. What it does is it just goes through the list of edges and one at a time tries to add them to the graph if it can. Now, it's not allowed to add an edge if it produces a graph that's not a tree by creating a loop. So you add edges as greedily as you can, but you're never allowed to create a loop or a cycle because then it wouldn't be a tree anymore. However, to make the greedy part of the greedy algorithm work, you need one little trick, which is the edges have to be in the right order when you do your greedy thing, which is sorted from smallest weight to largest. So greedy means we're going to try the smallest weights first, and if they work out, we keep them. We want to avoid edges that have high weights, so we put them off as long as we can. And so now we loop through the edges in sorted order. And for each edge, let's call the edge UW so that I have some variable names I can work with. So we're processing an edge that connects from U to W. I'm going to call that 4A. This is inside the loop. If U and W are not already connected to each other by a path in the graph, connect them. Now you notice that this doesn't say if U and W are not connected by an edge. It says if U and W are not connected by a path in the tree that we've formed so far. And so two vertices might be connected by a very long path in that tree. So I have left out a very important question here, which is how can we determine whether U and W are connected to each other by a path in a way that's fast? Well, I've shown you one way to tell whether U and W are connected to each other, and that's to use depth-first search in T. But that takes linear time, and we can do better than that. But it's going to take another lecture to show you how to do it really, really fast. And so that'll be lecture 33. But for the moment, I'm going to put off how we do step 4A. Now, let me point out a few things about this algorithm. First of all, because this algorithm never adds an edge, UW, if there is a path that connects them already. T is guaranteed to be a tree. Well, that is, if G is connected. If the original graph is not connected, then there's no way the spanning tree can be connected either. So, but in that case, we at least get a forest. Yeah. Well, for now, it's depth first search. So for today, just assume we do this by depth first search. And then a few lectures from now, I'll show you a faster way that's called the disjoint sets algorithm or the union find algorithm. Other questions? By the way? All right. So what I want to try to do, if I can get this right, is to run this algorithm on a piece of paper. So here's what the algorithm does. Here's a bunch of airports and the number of miles that connect them. I believe this is in the Goodrich and Tomasia book. And so what we're going to do is we're going to go through all the edges in sorted order and just try to add them to the graph. So initially assume that we have none of these edges are part of the minimum spanning tree. So we visit them in order. The first edge, the one with the lowest number, is 144. And since I'm doing this by eye, I might get it wrong, so if I make a mistake, please someone shout out. But 144 looks like the smallest edge, so we're going to add that to T first. This is now officially an edge of T, our first edge. Then we go on, what's the next largest edge? I think it's 184, so we can connect these two, since they're not connected by a path yet. The next largest edge is 187. Boston and JFK are not yet connected, so I connect those. What's next? 337. So SFO and LA are not connected yet, so we connect them. After that, I believe 621 comes next. So ORD and BWI are not connected yet. Let's see, is 740 next? Okay, so 740 would be our next edge, but this is our first loop. See, ORD and JFK are already connected to each other by a path that goes through BWI. So we cannot add this edge. This edge does not get added to T. Then is 802 next? All right. So Dallas-Fort Worth hasn't been connected to anybody yet, so we can add this edge. Then there's 849, I believe. But there's already a path connecting ORD to PVD, so we can't use that one. 867, well, there's a path from Boston to ORD. Anyone know which airport ORD is? O'Hare. That can be right. Yeah, that makes sense. And 946. Well, Miami hasn't connected to anybody yet, so let's put that in. 1090 would be next, but JFK is already connected to Miami through this path, so no, we don't add the 1090. And 1121, well, Dallas-Fort Worth has a connection to Miami. 1238 is next. So we connect Dallas-Fort Worth to LA. And now you can see it's a tree. Every airport is connected by now. So all of the rest of the edges are going to be rejected. And that's Kruskal's algorithm in action. So let's look at the running time of this. So step 2, well, step 1 is just going to take order v time. So I'm not even going to look at that because it's going to be overwhelmed by other things. Sorting E edges. How long does it take to sort edges? Well, it depends what algorithm you use. We're going to investigate a number of algorithms over the next few weeks. We're going to do 5 lectures on sorting. But I can tell you that the most commonly used algorithms take E log E time. Though under the right circumstances, you can actually do it in linear time in the number of edges. And so that's going to be one of the dominant parts. Then actually, I guess that's step 3. And then step 4, well, we're going through all the edges. That's going to take order E time, which is dominated by this. And then step 5 is the tricky one. But so right now, if we just use depth first search, this step might take n squared or v squared time. Question? Oh, 4a. I'm sorry. I'm getting all my numbers wrong here. This step here. Yeah. So figuring out if things are connected. And if I use depth first search, that could take order v time on average. And so it might take order v squared time overall. But we're going to learn a better algorithm for that that's much faster in a few lectures. And that part will take less than big O of E log E. And that's coming up in maybe a week or so, too. And those are the main costs of the algorithm. So adding those together, Kruskal's algorithm runs in big O of, well, actually I need to add the v here. So let's say steps 1 and 2 take order v time, even if there are no edges. So adding those all up, we have an algorithm that runs in v plus E log E time. And one thing that you can write this in maybe a slightly simpler form because E in the worst case is at most v squared. And if you take the log of v squared, that's the same as 2 times the log of v. And the 2 doesn't matter. So that's the same as big O of v plus E log v. So this way is maybe a little easier to grasp. All right, since I have a few minutes left, I want to say a few words about why this algorithm works. There's a proof in Goodrich and Tomasia of why this algorithm will always give you the minimum spanning tree, and I encourage you to read that. I want to give you the high idea right now. So suppose I have my graph. Now, this graph is the graph T in progress. So this is T while I'm building it up. Maybe I'm halfway through running that algorithm. And maybe this is what T looks like at a particular moment in time. And so now I'm looking at a particular edge, UW. Suppose that has a weight of 4. And I'm deciding, should I or should I not add UW? Well, I want to define two separate sets of vertices. So I've got this big set of vertices. I want to divide it into two separate sets. There will be a set that I'll call capital U. And capital U includes little u and all of the vertices that are connected to it by paths. So big U is this subgraph of T. It just contains U and the vertices that are connected to it. Yes? Oh. Thank you. Gee, I even drew that in my notes, man. Right. No loop. So big U is going to be all the vertices that are reachable from little u. And big W is going to be all the other vertices. All right? Now, if I have a spanning tree, by the definition of spanning tree, all of the vertices are connected by a path. So I'm going to have to add at least one edge in my spanning tree that connects U to W. There has to be an edge from this set to this set. The question is, there has to be at least one edge from that set to that set. The question is it safe to choose this particular edge? Well, remember, I've sorted the edges by weight. So if this is the first edge that I've looked at that connects this set to this set, then all of the other edges that connect those two sets that I could consider instead have a weight at least as big as 4. So maybe there's an edge there with weight 5. Maybe there's an edge there with weight 6. Maybe there's even another edge with weight 4. That's okay. But the point is, it is always safe to choose this edge. Why is it always safe to choose this edge? Well, any spanning tree has to have at least one of these edges, because U has to be connected to W. If I had a spanning tree that had this edge, but did not have this edge, then I could reduce the weight of that spanning tree by taking this edge out and replacing it with this one. So if I had a spanning tree that uses this edge, but does not use this edge, I can make a better spanning tree by swapping them. Get rid of this one, put this one in instead. And so I can guarantee that there is some spanning tree that contains this edge. Therefore, when the algorithm greedily takes this edge and puts it in, it's safe to do that because there is a spanning tree that contains that edge. And that's the foundation for the proof of why this algorithm works. And if you want to see all the details, again, I encourage you to read Goodrich and Tomasia's proof in full. Any final questions? All right, well, congratulations again on finishing Project 2. And on Monday, I will teach you 4 algorithms for sorting numbers.